going to go ahead and get started. Frank is also, as Jacqueline said, in California, so it's nice and early for him. So I do definitely appreciate you waking up for us today. So Frank, with that said, I'm going to go hand it over to you.
My name is Griffin. I'm director of the Diego Supercomputer Center, and I'm here to tell you a little bit about the lessons learned by SDSC on composable infrastructure and the rationale. There are, in essence, two reasons why we are interested in composable systems. One is about the social organization of computing, the software user environments, including resource allocation mechanisms, have become diversified. Different communities have different environments that they work with and different allocation mechanisms that they expect. We want to make the same hardware available to as many modalities of use as possible. This includes traditional HPC via Slurm, containers via Kubernetes, and bare metal via testbeds like Chameleon, Cloud Lab, Fabric. And we had, once upon a time, a mechanism that we developed ourselves for being able to do this kind of environment switching. And that was bare to maintain. And so we chose to select right Autoscaler technology instead for Expanse and NLP systems at SDSC, where on Expanse we switch between traditional HPC via Slurm and containers via Kubernetes. And on the NLP system that is coming this summer, we intend to switch between all three of these, Slurm, Kubernetes, and Chameleon. In addition, we see an increasing hardware diversification. The market today offers us a dazzling set of hardware choices to compose into host systems. There is these 6 different exciting Aveo cards, there are multiple different Ampere-level NVIDIA GPUs, not counting the myriad of older cards still around, gaming cards, RTX, AMD, Intel GPUs are coming in too. There's DPUs for multiple vendors, ranging from Smart NICs to GPUs or NICs to FPGA NICs. There's a variety of different CPU host systems, faster but fewer cores versus slower but more cores, different vendors, different architectures, ARM versus x86. And then, of course, there's different amounts of NVMe that one might want in hosts for different purposes. And all of this it's just not scalable to have different hosts for different purposes and have them all as distinct hardware and as options for users to allocate to. And so what we instead want is we want some of all of these, and then we want to dynamically compose different devices into different hosts, and therefore be able to dynamically compose different and reconfigure hosts with different devices for different applications on the fly. And we believe that we will have that kind of capability and we'll implement that kind of capability starting in, this summer with GigaIO. And the project that where this will come into play is the National Research Platform. What you're seeing here is the national scale infrastructure layout. And in the circle around San Diego, there'll be resources including 32 Alveo FPGAs, 64 NVIDIA A100s, 80 gigabit, and 350 terabyte of NVMe. And all of that will be a number of different, 5 different CPU hosts, and all of that will be in a GigaIO platform, and you will be able to compose them into different host environments. A100s with FPGAs, FPGAs with CPUs from AMD at different speeds, different amounts of NVMe, etc., etc. And I hand it over to the next person.
All right, appreciate that. So what Frank talked about a lot in the first part of the presentation was the complexities you're going to find with heterogeneous compute, right? I'm trying to solve lots of problems with today's technology. There's no one size fits all, right? So we're going to deal with lots of different types of resources, right? Different storage capacities required, different memory capacities, different GPUs, FPGAs, DPUs. I mean, there's a lot of PUs out there right now at this point, right? You have RPUs and IPUs and so many different types of devices, right? These are all, well, and other problems not getting smaller anytime soon, right? In fact, there's a lot of companies out there getting ready to create their own new accelerators. And last count was 204 stealth mode accelerator companies. So with that massive amount of growing devices, right, the challenge that comes with heterogeneous compute is only going to get harder. And so for Frank, putting him in a scenario where he can be flexible to go pick and choose how many of what he needs to go run each workload is a massive advantage, right? Here we're going to talk to you about how we do that on the GigaIO, and that's done through the power of our memory fabric. So memory fabric, you're probably going, what's a memory fabric, right? I've heard of InfiniBand, I've heard of Ethernet, right? Many of you have heard of PCIe fabrics, right? Which is ultimately what we kind of ride on. But for us, what a memory fabric is everything in your system has memory, and so we're just this interface that allows you to connect all those things together. And I'll kind of get to that a little deeper here. So ultimately, the problem that we're solving is there's a massive amount of data growth going on right now. I think everybody knows that, right? With that data growth comes a whole new set of solutions we can go pull out of these problems that come out of this data. So a lot of customers are driving towards the cloud, saying, all right, if I have all this data, how can I stay flexible enough to put myself in a scenario where I'm always ready to go solve whatever new challenge I'm trying to drive towards? If I buy a system and it's 3 years old and I have a new type of data or I have a new way to go find a resolution from that data, is my 3-year-old hardware going to cut it? Right? If I go to the cloud, I simply go to a website and I say, hey, I want to have this new node type with this GPU type, and I want this many, this much storage, this much memory, and I've got a new system ready for me. Right? It's very, very flexible. So you're seeing a drive towards that in this HPC and AI industry for that reason. Right? How do I stay at the edge of technology? Well, I don't pay for that hardware, I rent it. Right? I use it as I need it so I can maintain my flexibility. The problem that comes with that is the cost. Right? I think all of us that have used it have gone, all right, well, that was a great idea the first time. Then I got the bill, and it was a little less appetizing for me. I heard moving 10 gigs of data from one location to another across the cloud was over $10,000 for 10 gigs. Right? This is something that goes on little USB sticks now, and it costs me $10,000 to move it. That's pretty absurd. Right? Then you add GPUs and CPUs in there, especially in the GPU realm. Right? Those prices can be very hard and very hard to digest. As I mentioned before, lots of different types of accelerators. Today we're seeing just FP16, 32, 64, embedded GPUs, a vast growing array of FPGAs, vector engines, things like that. Computational storage is on a big rise. And then you get a lot of different technologies, right? You have your nickel and your RICL rings going up. Everybody's trying to add new software capabilities into all these different hardware packages. So it's not as easy to just buy something and just expect it to work for everything. So what we do at GigaIO is we kind of take that traditional rack, which is your traditional service here, full of resources, right? This is a pretty simplified version of that. And then we go ahead and we offer a couple different ways. But the first way we do is we actually disaggregate some of that hardware. We disaggregate it to resource pools. Then we go ahead and send that into our Fabrics software. And that allows us to create new bare metal servers that look exactly the way you want them to look. So in this scenario here, I'm going to go run a unique workload, and that workload says, hey, you know what, I can really use 3 FP64 GPUs for this job. So I went ahead and literally pulled 3 FP64 GPUs out, connect them to a server, connected the right amount of storage, the right amount of memory around that, and then I go run that workload on that. And I did that in a matter of seconds. So I didn't have to go send an intern down to the lab and go ask them to go, hey, go find a box that'll fit this, go find these right cards, try to go plug them in here. None of that had to happen. I simply sent an API, and it's done. Or in this case, I actually used Bright Cluster Manager to go ahead and in the GUI or in the CLI, just simply drag a host to a GPUs and off and running. Then you see the next example, right? We're talking about an FP16 GPU. And then the third option, right? This is a cluster of servers. So here I actually composed the resources to this cluster of 4 servers. And not only did I create 4 brand new servers with all new physical hardware, what we're also able to do is use this memory fabric to interconnect those together. So I'm not just delivering devices to servers, I'm allowing those devices to all talk to each other, whether they live in the same server, whether they live in the next server, anywhere else in the rack. If I have GPUs living in, or any device living in any server, I can go talk to it directly, whether that device is living with me or composed to me or not. Because everything's connected via memory, so everything in our memory fabric can be accessed by anything else. So this server one on the top left can talk directly to the GPU in the bottom right, even though they're composed to two completely different servers. So what this drives is the ability to go create an impossible server. We've actually composed 32 RTX 6000 GPUs to a single one-use server before. Right? And you go, well, physically that obviously can't work, right? There's not a physical space in the one-use server. There's not a slot to the motherboard. That doesn't matter anymore, right? All those limits are gone. What we're able to do is go run a job, try it on 2 GPUs, then try it on 4, try it on 6, 8, 12, and we find where that curve starts to taper off. We say, hey, you know what? Best bang for our buck, right? We get the most performance, the best wall clock time for the right with using this exact number of GPU before we start wasting money to get a little bit more wall clock time, or a little lower wall clock time. We find exactly where we want to be, and then next time we know exactly the profile we want for that job. And we never have to go buy systems to go figure out what that is. We just simply compose the right resources for the right test at the right time. So again, this memory fabric concept, right, is more about, like I said, delivering resources anywhere throughout this rack. So we honestly think about our memory fabric as, instead of having 1U servers or 2U servers, we have 42U servers, right, where the server literally can consist of anything you want within your rack. So if I want to have GPUs that are living inside server 1, I can go talk to that directly. I can take that as if it's my own. Right? If I want some of its memory, I'll take that as my own. If I want a resource living inside one of these resource chassis, I'll take it as my own. Right? Same thing with our shared memory pool. So whatever type of device you want now, anything within your rack, I can go bring it to my server and go let my workload or access it directly as a direct memory access device. So what ultimately we're able to do is go have any node talk to any other node. And this is even using other protocols like TCP or MPI or libfabric, other types of protocols like that. We can any device can talk to any device, and any node can talk to any device. So it truly is a broad, wide-reaching memory fabric that goes full rack scale. So apologies because this was not my slide. I was actually a last-minute plug-in because my counterpart got COVID this morning. So he is not here, and I'm here. So this slide I have not actually seen yet, but ultimately what we're doing here is everything is memory mapped. Okay, so what that means is when I look at my server rack, I'm going to actually see all the memory bar space from every single server within my rack. And so that means if I have a device attached that to a remote server, I can say, hey, you know what? I've got my server A. I want to talk directly to the memory map location of server 6. This memory address to this specific device. And then when I go talk to it, because I talk through a memory fabric, I'm not required to go talk to the operating system. I actually go completely around that through the memory fabric directly into the device. It allows me to completely bypass the host kernel, allows me to bypass any additional bounce buffers, any memory bounce buffers. It is true DMA from one device to another device across that fabric. So like I mentioned the 42U server, right? Everything composed on a 42U server, and then we can go wider than that. If I want to go to multiple racks within a fabric, I can do that. So, but the difference being is, I showed those resource chassis earlier, where I have devices living inside them. I can compose any device to a server anywhere within that rack, and then if I want to go to racks beyond that, I just talk to the memory of all those other devices directly. And it allows me to go scale much wider than a single rack, even though I can compose everything with my rack. So physical hardware connectivity, how it works. We do operate across PCIe, but there are a couple other PCIe switch options out there. The difference being is we've integrated a technology called non-transparent bridging. And what that allows us to do is that's what allows us to communicate at that memory level. So PCIe lets me go move a device from here to here, right? I can do that all day long, right? And that works, that's pretty easy to understand. But then when you take the non-transparent bridging side, and now I've incorporated the memory aspect of every device and every server, now it becomes a much bigger challenge that we're solving, because not only am I able to go deliver a device, I can allow those servers to talk to each other, let the nickel ring work across that fabric. It really kind of unlocks a lot of doors that simple composition doesn't solve. So here we're plugging these servers into this memory fabric across this PCI switch. From there we go and add our accelerator cooling appliance. This is going to be just a box full of GPUs or NICs or whatever types of devices you want. They go to these purpose-built chassis that are meant for cooling your devices, uplinking your devices, and just delivering access to raw device, no CPU living inside these. And then we have our GPU servers. This is going to be like your DGX, your HGX box, right? This is going to be servers all converged within the box. But again, because we talk memory fabric and not just what we call simple composition, I'm able to talk to those GPUs the same as I can a GPU living in that accelerator appliance. It doesn't matter to me. Whatever environment you have, whatever GPU you want to use, whatever FPGA or NIC or storage, we will incorporate into the fabric and allow you to access anywhere throughout that memory fabric. We drive into storage, which is your storage pooling appliance composing NVMe, and then ultimately get into NVMe over fabric using VLANs, and then lastly our memory pooling appliance. So this is something newer that we're launching, which is going to give you the ability to actually compose DRAM to servers and share them between servers. So right now we're entering beta mode in this realm, but what we're really trying to drive towards is as CXL comes closer and closer, right? We're already doing this capability. We're already moving memory from one server to another server. We're already increasing. In fact, you'll see in the demo downstairs. We take memory away from one server, we give it to another server, run workloads on that memory, and you're able to go utilize that effectively. So we'll just skip that. So Northbound integrations are super important to us, right? We actually are meant to be invisible to the user. And that is why Martijn is here, right? Because they built one of the best integrations into GigaIO. And that is because we want to, like I said, be invisible, allow you to use your standard management application the way it's meant to be used, and just work natively. And so next I'm actually going to hand this over to Martijn, and he's going to go through a Bright Cluster Manager demo showing you how you compose your resources and utilize this memory fabric within the standard Bright Cluster Manager constructs.
So, I always like to start my presentations with a small bright intro in case you're not familiar with our product. So we built a project called NVIDIA Bright Cluster Manager. So it's basically a tool for system administrators to turn a pile of hardware into a fully functional cluster. So we streamline the whole deployment process, and after the cluster has been deployed, we allow administrators to manage, monitor, and health check the cluster in a very efficient way. So there's a couple of third-party software that we integrate with, Kubernetes, for example. So we're seeing a lot of activity in Kubernetes, and we've been integrating with Kubernetes for several years now. Ceph for storage, several HPC schedulers, such as Slurm and a couple of other ones, in order to run batch jobs. And then Jupyter to provide a convenient interface for end users to get workload up and running on the cluster. So at the heart of our solution, there is a cluster management daemon that's running on all the nodes inside of the cluster, and these daemons are interacting with each other in order to make the cluster manageable. And the cluster management daemon that is running on the head node or head nodes of the cluster is also exposing an API to the outside world that tools can interact with. So we have a BrightView management tool, which is a graphical management tool, and we have a cluster management shell, which is the command line equivalent. You can also talk directly to the API, either using our Python bindings or by making native JSON RPC calls, or by leveraging the Ansible module collection that we make available. And it's possible to build clusters on-prem, in the cloud, hybrid clusters, or clusters that span to the edge. So you can create a very large, geographically distributed environments that are all managed as a single large cluster using Bright Cluster Manager. It's very easy to repurpose nodes, so a node that is running Slurm right now could be running Kubernetes a couple of moments later. And that can be done automatically based on the workload that's being submitted to the different workload engines of the cluster, or it can be done by the administrator. And lastly, we also provide a rich collection of HPC tools and machine learning tools and libraries to make it as easy as possible for the users to get their workload up and running. So now on to composable infrastructure. So we came in touch with GigaIO probably a year and a half ago, and I've personally always been very excited about the idea of composable infrastructure because it gives you a lot of flexibility around composing the servers that you need to run a particular type of workload. And I always envisioned that we could add great value here because we can make that functionality accessible. So that's what we did. We released Bright 9.2 back in April of this year, and it has the first stage of GigaIO integration. And I'll explain to you what that means. So it allows, as Matt already explained, it allows PCIe devices to be pooled in so-called resource boxes. and then you can assign those PCIe resources to nodes dynamically as you see fit. So Bright streamlines that whole, basically everything that you need in order to use that effectively. So initially, you need to select a topology and then initialize the fabric basically. So Bright allows you to do that from inside of the Bright view or cluster management shell interfaces. And then after you've done that, you can start composing and decomposing resources or nodes. So we can do that manually right now. So an administrator can say, I now want to bind these resources to these set of nodes. And in the future, we want to make it possible to have bindings be made automatically based on the jobs that are being submitted by users. So I'll say a little bit more about that in a couple of minutes. So the nice thing is all of the hardware, all of the GigaIO hardware shows up as devices inside of Bright's cluster management infrastructure. And that means that we can also monitor those and we can health check those. And it is also important to realize that clusters may have several distinct fabrics that can exist in parallel with each other. So in most cases, you're just going to have a single fabric consisting of a number of switches and resource boxes, but you can also create a setup where you have multiple of those fabrics, and you can manage those from Bright. So here's a screenshot of Bright View. I'm on the big screen, it looks a little bit more readable than what I'm seeing. So in the middle, you can see the list of fabrics that have been configured. And then when we go to one fabric, you see a settings tab, a topology tab, and a bindings tab. And we're looking at the topology right now. So this is a 2S4x4 topology, which means that you have 2 switches, 4 nodes, and 4 resource boxes. And then the one is just an index because you can have multiple configurations like that. And each topology has a number of parameters that need to be set, most notably the switches and the resource boxes and the nodes. So this screen allows you to configure that from inside of Bright. Once you've done that, you can start making bindings. So we're looking at the bindings tab right now. And it's super easy to make those bindings because you just drag and drop the PCIe resources on the nodes, and then that will cause Bright to talk to the GigaIO switches in order to make those bindings. So the switches have a Redfish API that we're interacting with. So and we're using colors to show what is bound to what. So in this topology, we're looking, you can see that there's 2 switches. Node 20, 21 are on switch 27, and then node 23 and node 24 are on switch 28. And each of those has its own color, and right now no bindings have been made yet. And then on the bottom you see these IO44, IO45. Those are resource boxes that have PCIe resources inside of them. So when we start dragging and dropping either nodes on the resource boxes or resource boxes on the nodes, we can start making bindings. So right now, using the colors, you can see that node 20 is bound to IO44, and node 21 is bound to IO45. And then there's a little icon that you can use to unbind those. So here's a different topology. This is a 2S4x4 so a different index number, and you'll see that it has a slightly different configuration. So in this case, all the nodes are on one switch and all the resource boxes are on another switch. And it is necessary to, when you want to bind a node to a resource box that is on another switch, you have to use cascade links. So that means that you first drag a node on a cascade link. So in this case, we dragged it onto the one on the bottom that's now showing up in red. That also causes the other end of that cable to show up in red on the second switch. And then you can start binding resource boxes to that cascade link to make a connection between the node and switch. And the reason why that is not, you might argue that we could figure that out on our own, but there's actually multiple configurations because, as I'll show here, it's also possible to use multiple cascade links in order to increase the bandwidth that you have between the node and the resource boxes that you're binding to. And in this case, you can see we're binding to all of those resource boxes. So that node 15 over there on the switch 09, it may have a ton of GPUs being associated with it right now. And in this case, we're also binding some other resources to, we're binding the last two resource boxes to another node. So you use the colors to figure out what is associated with what. So I'm not going to show the cluster management shell interface here. This is all right. You can assume that everything that I'm showing over here can also be done from the command line, and it can also be scripted. So some future work. So one thing that we haven't done yet is to provide insight into what exactly is plugged into the resource boxes. That's because that required some extra Redfish API calls to be added, which now are available in the GigaIO switches. But we have to start using those. So that will show up soon. And the big thing that we want to do is to allow bindings to be made automatically based on the job requirements, because being able to do this as an administrator is nice, but having it be done automatically based on the jobs that users are submitting is even nicer. So ideally you want to allow a user to submit a job which requests 8 GPUs, for example, and if that node is not available, it should be bound, it should be created, composed automatically. So we have a tool which is called Autoscaler, and we're currently using that tool mainly in cloud use cases, where users are submitting jobs, and then if the resources are not available, then those jobs will not be scheduled by Slurm, for example. And Autoscaler looks at those jobs that cannot be scheduled, and it will create nodes in cloud, or it will power on more nodes inside of the data center in order to allow those jobs to run. So you can also use it as a power saving tool, because it's going to power off nodes that are not in use, and it will power on nodes when those nodes are needed. So our plan is to extend this Autoscaler to also identify jobs that cannot be scheduled because the right PCIe resources have not been added to those nodes. So for example, if the job requires 8 GPUs and there is no node that has 8 GPUs, we want to dynamically create a composer node that has those GPUs, and then the workload management system will be able to schedule that job. So that's quite a bit of work. It sounds fairly easy, but it is a lot of work, because we have to create a resource scheduler that looks at which PCIe resources are available, and then we need to do that in an intelligent way, so that we don't bind resources that are not necessary. So that's work in progress. We hope to either deliver this as an update to Bright 9.2, or if that's not possible, we'll deliver it in the next version.
All right. So many of you may have heard of composability in the past, right? HP put it out a long time ago with their Synergy product, right? They talked about composability, and then you had DriveScale that was doing some composability for a while before Twitter brought them up, and then Dell brought in some composability aspects into their blade chassis. But where they all kind of fell short was this whole concept of, in their mind, composability was about storage, right? It's about delivering storage to a server. And the reason why is because delivering storage to a server is easy because the latency doesn't really matter that much, right? If I live in the world of 10 microseconds to go deliver storage, the storage is slower than that anyway. You're not going to notice a difference, right? And so when you see the challenge of all these other items in here, right? Your networks, your CPUs, your memory, your accelerators, right? Living in microseconds doesn't work, right? Everything there lives in nanoseconds. And so that's why we've then kind of tasked ourselves with, hey, how do we get the rest of that stack? And that's why we operate in that PCIe memory fabric versus Ethernet, right? If I live in Ethernet, I couldn't do this either because it's just too slow, right? So you'll see some of the design decisions were all wrapped around making sure our latency is low enough to give you good, strong performance, while at the same time you'll compose all these different devices without them throwing up on you because it's just too much latency. One key point here is you'll notice at the very top there, that memory aspect, right? You'll heard a lot about CXL. CXL is coming strong. We're all very excited about it. It's going to take a little while for CXL to really take on and be heavily utilized. But we've actually been doing a lot of the CXL type capabilities already, right? So CXL.io capabilities all those functionalities within that. We've kind of been doing a lot of those to this point. You'll see that in the demo downstairs, actually. So composing memory is a big deal for us. Not only from the ability to just move memory around, but also when you think about today, if I want to go get an I/O from one server to another, I've got to go actually move that data, right? Now, if I can talk memory to memory, I just steal it from the memory of another server. I know exactly what's going on there. I can literally read, as it's writing to its own memory, I know what just happened. I can cut down on I/O significantly. I can reduce latency across the board because I'm operating in the memory world versus bringing everything down, reading, writing from disk, moving it from disk to disk, not having to do all those types of things. We've been a founding member in the CXL consortium, right? And that's why with CXL we are excited to see all the coherent capabilities we'll have with the CXL integration, and we're definitely looking forward to it. We will be a very early provider of the first CXL networks out there. You're seeing CXL 1.1 come in servers launching the end of this year, and shortly thereafter we will actually have a full CXL enabled product to be able to deliver CXL memory, CXL capable devices throughout the fabric. Some of the key benefits, right, are optimizing CapEx and OpEx. So one thing you talked about, right, what Martin talked about was adding 8 GPUs to a box and then have one. Well, the other part of that is, if I only want 1 GPU, and if I only bought nodes with 8, right, or I only want 2 GPUs, I don't want to have to waste all those GPUs sitting in that box, right? Or what happens when I want to try a new card? Do I have to buy a whole new server, a whole new infrastructure to go try a new card, right? Or I can just put that card inside the resource chassis and deliver to whatever server I want to, right? It gives you a whole lot of flexibility, and it really helps you manage your CapEx. When things are getting older, and I want to update, do I update just my server? Do I update a whole stack? Do I update just my servers, or just these GPUs, just this disk, right? It completely changes the way I have to buy because I've disaggregated those resources. Right? Again, pay as you grow, add the pieces in that you need. Don't replace the whole thing at the same time. Impossible servers, again, up to 32 GPUs in a single node. That's actually where CUDA stops, right? CUDA doesn't work after 32 NVIDIA devices in a single server, so you have to go beyond one server at that point. But we've actually done that today, right? We've gotten 32 RTX 6000 to a single node before, kind of proving that out that it actually can hit that level. Reducing power, because of the fact that we put a lot of these GPUs in resource chassis, we cool them better. If I put them in a server, which still, again, fully supportive, if I have everything in a server, that server is competing for heat or for cooling with my CPU, my memory, my disk, and my GPUs, right? Nothing's cooling optimally, so nothing's running as efficiently as it could. If I disaggregate, I put them in purpose-built chassis all around cooling them, guess what? My CPU runs better and my GPU runs better. And then here soon, you're actually going to see immersion-ready chassis coming out from us to even increase that even more, right? So we can go be immersion-ready as we kind of work through the sustainability issues and the global warming problems. So, kind of some key use cases. University of Toronto, right, one of our customers, they are using this because they want to have multiple different schools of technology that are utilizing the system. But you're going to see grants coming for X, grants coming in for Y, grants coming in for Z. How do I make sure that I can put an infrastructure together that's going to be managed appropriately, be high performing, have a high performing network, and actually get more for my money because I was able to go merge everything together? If I allow just one grant to go, and it's going to go into somebody's closet, and it might be used for that grant somewhat, and then it's going to kind of die, right? It's going to slowly degrade and become irrelevant, right? If I'm able to pull these together into one bigger system, and then implement something like GigaIO, where I'm able to go dynamically compose exactly what they need when they need it, it puts them in a scenario where if I want to try something new, the incremental add to the fabric to go make something new is small. So if I want to go try a new type of resource, I can just simply add that one resource in, and it can take advantage of the whole power of the entire system, right? And if somebody else says, hey, you know what, I purchased this, I added this to the fabric, I want to go try this, but I'd also, hey, what happens if I add a little bit more of this? There's other resources there to go pull from, and they can compose it real time. You can even charge back on those things. Where, hey, you know what, if you're going to pull from the free resource pool, maybe we charge you a little bit extra to go do that, right? Because you're going to go utilize more resources. All those things are now possible because we've disaggregated and then we've added to that memory fabric. Here's what we're doing with SDSC, as Frank mentioned earlier, and creating this distributed architecture. We're going across the country and be able to solve lots of different types of problems in different locations. So we're trying not to have to move the data around so much, right? Get it to local spots, and go process the data more effectively, getting the right resource to that data. And then here we're also doing it with UT Austin, right, for their TAC environment. This is part of the Lone Star 6. It's a portion of it today. They want to be able to really dive into the NEC vector engine capabilities, at FPGAs, and then having different types of GPUs. They want to see what that heterogeneous compute environment can really do for their customers. As these users put their jobs into buckets, they want to give them more diverse buckets to choose from. So when they have to use their credits to go do workloads, they're getting the right devices, they're getting the right containers to go meet that actually solve that problem. Yeah, and so the future of composability does look bright, right? See how that works there? Right? We don't have to be single focused on our clusters, right? That's one of the big things I want you guys to get out of this is we're all about heterogeneous compute now, right? And that doesn't mean that I have 2 GPUs in my environment. It doesn't mean I have 2 different types of networks. It means I have all those things. I have lots of different GPU types, CPU types. It doesn't matter if you want to try out ARM, you're using Intel, you want to have AMD. I don't need to have a stack of ARM, a stack of Intel, a stack of AMD, each different GPU type. I put the CPUs in, I put the other accelerator resources in, I compose them where they need to go. And that's me really go increase my flexibility, go try whatever software I want to go try on it, and mix and match as needed to meet the customer demand, right? Latency sensitivity is really important. That's why everything runs in that nanosecond range. So I can keep this flexibility while maintaining a high level of performance. All right, well thank you everybody, I appreciate it. If you have any questions, feel free to reach out. Again, my name is Matt Demas here at GigaIO. Thank you Martijn and Frank for joining us. Yeah.
So you're looking at racks that have got heterogeneous stuff in it, which is connected to your node, presumably used by different users, different workloads, and so forth. As this systems get bigger, how do you handle the sort of contention on that fabric? And how severe is that impose proximity constraints on what you activate what and so forth?
Yeah, no, great question. So that's where the composability aspect, the composability range, where I can actually move a device from a resource chassis to server stage to the rack, right? And so that's where things like Autoscaler are able to go say, hey, let me go make the most efficient choice here, right? So if I'm going to go pull a GPU, if I want A100s, right? I don't want to pull them from this from way up here. I'm going to go pull them from the resource chassis closest to me to keep the amount of bindings as small as I can and keep everything as close as possible. The host-to-host communication, that's actually going to be on a dedicated channel. So if I'm going to go pull from the memory of another host or pull from a different host, it actually goes across a different crosslink altogether so that we can isolate composability traffic from traffic going memory to memory between servers. So if I'm going to run nickel rings across my environment, for example, right, I'm going to make composed GPUs in each server. They're going to run across their own links. And then the nickel aspect will actually go across a completely different crosslink in that environment. And we do that for that exact reason, right? We don't want that GPU communication to contend or cause contention with the node-to-node traffic. Yes?
Question about the scheduling aspect. So does this right on the schedule look at the queue and then look at jobs that are close to being one on top and then start to create those clusters, or is it wait for jobs actually start executing?
Well, the scheduler is not going to schedule the job until the resources are available. So Slurm will put it on hold basically, and then Bright detects those jobs that are waiting to be scheduled because the resources are not available, and then it tries to compose the resources to the nodes to allow that job to run. Right.
And then in a big cluster where there's no free resource available, typically how does it decide that someone
Then it cannot do anything.
We'll just wait until it's idle.
Yeah, I mean, you can do that in a naive way, and then the jobs may never run, or you can do it in a smart way, and that's what the tricky part is, doing it in the smart way, such that we don't make stupid choices in composing these nodes.
And then that's why the next part of the release is so important, right, to get it right, so that we can really help the intelligence there. And it's not just as quick as say, automatically create this, because you said it's very complicated, right? There's lots of jobs coming into a cluster, they're often oversubscribed, and making sure that you're taking the priorities and weights of every job coming in into account, as far as what's happening, and what I can actually go create. So that's a lot of the challenge that Martijn and the team have, and yeah, that's some integration with.
Is it something about the time it takes to create such a
Yeah. So the time is, if you're using synthetic endpoints, which I think most of our customers are at this point, they can take as little as 2 or 3 seconds to go ahead and compose new devices within them. If you're not, if you're using, in fact, I think the demo that he shows downstairs doesn't have those enabled, which means that you actually need to move the server between. But with synthetic endpoints, you don't have to.
Okay, you. Okay.
So I have a question about, we've had some online discussion on that, about SRIOD. Are you guys looking at scalable I/O virtualization, SIOD, and what the impact would be in terms of how fabrics can handle that?
So we are looking at the MRIOD aspects,
Yeah.
right? So that we can take a physical device, take the virtual functions, and distribute them onto different servers. So we have a new switching line being launched for the end of the year, which will be able to take advantage of that. So, for example, I'll be able to take potentially we'll take MIGs. I'm not certain MIGs are going to qualify underneath that, but I can take any virtual function, true virtual function or SRIOD function out of the device and go distribute to remote individual servers. So I can not only give you multiple servers or multiple GPUs or individual GPUs, and give you sections of GPUs spread out as needed.
So I was just curious about, I think the SIOD spec, so the Compute Foundation just got a few weeks ago. I think it's going up to 256 virtual functions, where before it was fairly limited.
Sure.
I think that involves doing the config space stuff on device or by microcontroller. So maybe we'll have to have an offline discussion.
Yeah, let's definitely.
Okay, sounds good.
Any more questions?
Yes, supposed to the scheduler, just the hypothetical composition. So you basically, normally when you have a scheduler, it knows that X, Y, and Z resources on it. In this case, you basically say, I have all my resources available, and then it will schedule a job like that.
Yeah, the GPUs, they are made available as resources to the scheduler. So the scheduler will know that whether there are GPUs in a node and whether the job is requesting GPUs. And if the GPUs are not there, the job will not get scheduled. So about different PCIe resources, that will not happen automatically, but that can be fairly easy set up using GREs in Slurm, for example, and other schedulers have similar constructs.
Okay.
Well, thank you, everybody. Appreciate it.